Okay, pre-calc nerds, we're going to go ahead and finish up Unit 2.7. So this is we've already started 2.7b, but we're going to go ahead and put a nail in this 2.7b coffin. We're going to get as deep as we can into it, and then after that, we'll call it a day. Start reviewing tomorrow, and reminding you that your next assessment is this Friday. Okay, so this lesson is about compositions, and I mentioned it yesterday, but it's actually going to show up finally today, that transformations are actually compositions of functions. So we can describe all transformations as compositions of functions. So here we have these three functions, f, g, and h. We're going to do the compositions that it's asking for, and we're then going to graph them. And we're just going to describe the transformations that have occurred to the function because of said composition. So this first one, f of g of x, is telling you to take this x minus 1, because that's g of x, and plug it into f of x. So where f of x had an x, it now has a set of parentheses, and then g of x belongs inside those parentheses. So if I'm color coding, okay, bless you. So for color coding, we get something like that. If we were to graph this, this is just a parent quadratic that points up, whose vertex is at 1, 0, because that's what makes the inside equal 0. So it looks like this. So how does that compare to x squared? Well, it's shifted right 1 unit. That's it. Describe the transformations, and then graph. Shift f of x right 1 unit. I guess the official AP version of that would be horizontal shift of 1 unit. Since it went to the right, it would say positive. So I guess we should write it that way, right? Horizontal shift 1 unit. Because they won't say directions in their shifting. For this one, instead of plugging in g of x, we're going to plug in h of x. Where f had an x, now there's a set of parentheses, and inside those parentheses, we get this. Okay, well, this actually can be described two different ways because it didn't shift the vertex away from 0, 0. The way it sits, you're being shown that it's a horizontal dilation, horizontal inside, right? So since it's a inside multiplier, we could describe it as horizontal dilation. But remember, horizontal inside opposite for Heilbas, horizontal inside opposite. So it looks like you're doubling your x's. You're not. You're cutting them in half. You could get creative, and you could actually square the 2 and the x and just call this 4x squared. And instead of describing it as a horizontal dilation of factor 1/2, if you said it was 4x squared, then you could describe it as a vertical dilation factor 4. Doesn't matter which one you decide, they have the same result because the vertex is still at 0, 0. Bless you. Gives us this. It's got coordinates at 1, 4 and negative 1, 4. And this one, take g, and where it used to have an x, you're going to drop in x squared. So g was my red one. It had an x here, and that's where I'm dropping in x squared. Well, that cleans up to this. That is just the parent quadratic that has been shifted down 1 unit. So its vertex is here. Vertical shift, negative 1 units. which means down. You know, they're not going to say up and down. They'll say positive vertical shifts for up, and they'll say negative vertical shifts for down. Sir?
You still gotta like graph it even though it doesn't say that you need to?
I only did it because the grids were here.
Okay.
On the test that you have this Friday, it's just describe the transformations. So as long as you can do that, you were in good shape. This picture is kind of confusing. F of x goes from here to here. This is g of x. So I don't know if you want to highlight it in color somehow to show that this is f, like that. Just so you can see that it didn't bounce off the x-axis there. That they're actually crossing each other. Well, this is g. So what we've been asked to do is we've been asked to complete the table for f of x and g of x, and that just means read the red and blue y values off of this. And after we've done these two columns, then we get to define h of x's values. And h of x's values are the composition of f and g. And then we'll get to graph h of x down here. Okay, f of x I did in blue. When x is negative 4, f has a y value of negative 4. When x is negative 3, f has a y value of negative 2. At x is negative 2, f has a y value of 0. And at f equals negative 1, excuse me, x equals negative 1, f has a y value of 2. So we can see for this portion of the blue line, f's rate of change is positive 2. Up 2, right 1, up 2, right 1. Now this line, we could have to read the graph, or you could just see that the slope is down 1, right 1, down 1, right 1. So we know this y value is going to be 1. This y value is going to be 0. And then after here, the slope is up 1, right 1, up 1, right 1, up 1, right 1. So back to 1, then to 2, then to 3. Just like that. Oh, you can't see what I wrote. Sorry. Time for G's y values. At negative 4, G has a y value of positive 2. And if you look, the red slope is down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, all the way until x equals 0. So it's going to just be decreasing by 1 as we go to the right. Now, at x equals 1, my red one's going to have a decimal slope. Rather than guess at it, let's look and see at x equals 2. We don't have a decimal y value. So at x equals 2, we have a y value of negative 1. And since it is a constant rate of change from this y value to this y value, hopefully you can see that it goes up 1, right 2, which is the same as saying up 1/2, right 1. So this is a 1/2 value. And then we have a slope of negative 1 again. So I'll get negative 2, negative 3. Just like that. Awesome. Red and blue make purple. So, hello, purple. So this is what this is telling us to do. H of x's y values are found by using the red g of x number as the input for f of x. So at x equals negative 4, what this actually says is f of g of negative 4. But this is g of negative 4. So this actually says f of 2. And f of 2 is 1. At x is negative 3, this says f of g of negative 3. but this is g of negative 3. So it's actually saying f of 1. F of 1 is 0. At negative 2, f of g of negative 2. But this is g of negative 2. So it actually says f of 0. 1. And x equals negative 1, f of g of negative 1. This is g of negative 1. So it's actually f of negative 1, which is positive 2. F of g of 0, that's g of 0, so it's actually f of negative 2. F of negative 2 is 0 again. This one might be kind of a pain in the butt. Let's see. F of g of 1, this is g of 1, is actually f of negative 1.5. So we have to go to negative 1.5 and go up. Luckily, this thing had a slope of up to right 1. So we know that that is exactly a 1/2. So what is that? Oh, it's at a 1. I'll be okay. Looking at a y value, right? I'll be all right. Kind of boring, all zeros, ones, and twos. We already know what happens when the red number is negative 1. How about this one? F of g of 3. This is g of 3, so it's f of negative 2. Oh, we already know that one too. And do we know this one yet? Or is this one new? This one's new. F of g of 4. This is g of 4. So f of negative 3. F of negative 3 is negative 2. And now we just get to plot the purple ones. These are x's. These are y's. So negative 4, 1. Negative 3, 0. Negative 2, 1. Negative 1, 2. 0, 0. 1, 1. 2, 2. 3, 0. And 4, negative 2. So this kind of question is really interesting to me because there's absolutely no way I ever would have been able to predict that composing these red y values into these blue values would have given me that. I mean, I don't know about you guys, but I never would have guessed that. It's neat though. You will be asked to do something similar on your test. Much less complex than that though. Much less complex. Or is it on the review? Now I can't remember, but the point is it's a lot easier than that. So if you can pull that off, you're in good shape. Any questions about it? It's tedious more than anything else. All right. It says for each of the following, we're going to compose them in both directions. We're going to do f of g, and we're also going to do g of f. We're going to find the domain of the first composition. Then it says to use a graphing utility to graph each composition function. I guess I'll do that on screen, but you guys know how to graph stuff. And then it says this, determine if the compositions are equal. I feel like equal compositions, since generally compositions are not commutative, should be something very special. Do any of you remember some types of equal compositions from your Algebra 2 days? What happens when those are equal to each other? No? Okay, well, we'll see it happen. We'll see it happen. Let's find f of g. So where f used to have an x, I'm going to open a set of parentheses. And that's where I'm going to drop in red g of x. It says to find the domain. And I told you yesterday, you find domains before you do any symbol simplifications. Are there any numbers that you cannot take the cube root of? Nope, there's not. You can take the cube root of anything. You know what that means? That means the domain is all real numbers. Now, you can't take even roots of negative numbers in the real number system. Even roots of negative numbers give you I, or powers of I, and things like that. But odd roots, third roots, fifth roots, seventh roots, whatever, all real numbers. So even before you simplify, this domain is all real numbers. Now let's simplify. Guess what cubes and cube roots do? They cancel. That leaves me with x plus 1 minus 1, which just equals x. Oh my goodness, f of g of x leaves just x. Almost like the f and the g cancel each other and leave just the x. Anybody remember what that's called? Well, we're about to find out if it's commutative. We don't know for sure. What do we normally call something when it cancels something else? Well, reciprocal fractions cancel each other, but what cancels multiplication? Division. And Barry just remembered the word is inverse. Because these two functions canceled each other when I composed them and left just the x, there's a really good chance that they're inverses. But the only way to prove they're inverses is to compose them in the other direction, because inverses cancel each other in both directions. Inverses are always commutative, and that's true for inverse operations and inverse functions. So now let's find g of f of x and see if it's also going to cancel. And where it used to have an x, I'll drop in the blue f of x. I should have used parentheses, but I chose not to because I looked ahead and I saw that those parentheses weren't going to do anything because there wasn't a multiplier in front of x. However, this negative one and positive one, those will cancel each other. Ta-da! So what we have here is that g of f of x is the same as f of g of x. Both results got me x. So because the compositions were commutative, but more specifically, because both compositions left you with just the bare x, these two functions are inverse functions. And f is equal to g inverse of x. Yes. At least for part A. That little symbol that looks like an exponent, that's the inverse symbol. These with the 1/3 and the -3 and the ×3 and the +3 also kind of look like inverses, don't they? Let's find out if they are. This is a great YouTube channel called Red Pen, Black Pen, or Black Pen, Red Pen. I can't remember what order he does it in, but it's this guy, he's a professor, and a young professor, and he writes in red and black dry erase markers, and he holds them in his hand at the same time, like this. And he writes with both of them as he's going, and does math in both markers. It's really cool. It reminds me of that when I'm swapping out my colors. Anyway, we've got this 1/3. We're going to throw red g of x in there. Red g of x is a 3x plus 3. When we distribute this 1/3, what it gives us is x plus 1 minus 3, which is x minus 2. We instantly know that these two functions are not inverse functions. Because in order for them to be inverses, they have to cancel each other and leave behind just x. But that doesn't mean that the compositions aren't equal. Maybe they are. Let's find out. Oh, by the way, these are both linear, so the domain is all real numbers. It's almost a moot point to even say. Anyway. So g had an x next to its 3, and that's where I'm going to drop the blue f of x. Now when I distribute that 3, I am going to get x minus 9 plus 3, which is x minus 6. Oh, so not only are this f and g not inverse functions, but the compositions are also not commutative. So we don't have to say it, but we could see it. We could see that these are not the same. It is interesting, though, that the compositions are parallel lines. That's interesting. But I think it's just a result of them having reciprocal slopes. Everybody's favorite. Time for word problems. Yay! The volume, V, in cubic meters of a weather balloon is given by V of R, meaning where R is the radius. The volume, in terms of radius, is 4/3 pi r cubed. That's actually the volume of all spheres, 4/3 pi r cubed. If the radius is increasing at this rate, so we have a function for our radius. Makes sense. I mean, when you blow up a balloon, if it was a perfectly round sphere, if it was perfectly spherical, every time you put a breath into it, the radius would get larger, right? So we have a balloon here that's growing in size. How do I know it's growing? Because anytime you cube a number that's bigger than 1, or bigger than 0, excuse me, you be careful about what I say here. I'm seeing the graph in my head. Yeah, it's an always increasing function. It says find the volume, but as a function of time. That means find V of R of t. That's what we're being asked to find. V of R of t. Because if we do that, time will now be the input, volume would be the output. So all we have to do is take our volume function, and where we used to have our radius, we write our radius function. Here's our radius function. Please remember that this is a product, which means I can apply this exponent to both of these objects. One half to the third power is 1 to the third power over 2 to the third power, which is 8. And when we raise a power to power, what do we do with the exponents? You guys can all just shout it out. When you raise a power to a power, you guys multiply your exponents, please. T to the 9th.
I got a question.
Yeah, what's up?
What if you didn't have parentheses between the two exponents?
If you didn't have parentheses between the two exponents, oh, you mean if I wrote something like this?
Yeah.
This is something completely different in mathematics. When you see it written, this is a tangent, but if you see it written like this, because of the order of operations, it is assumed that this is in parentheses. So that's actually x to the 9th, not x to the 6th. That's a good question though. So without the parentheses and you see exponents to exponents like that and there's no parentheses, the assumption is because of the order of operations, you always do powers first. So that is a power of that 3. I wasn't expecting that to come up today. And here, so just cleaning it up, we're going to have 4 over, oh, this is going to reduce, isn't it? 4 over 24 pi t to the 9th. 4 over 24 reduces to 1/6, right? So 1/6 pi t to the 9th. Interesting. I do a question very similar to that in my Algebra 2 Honors notes when I do compositions. It's a word problem about heart stents and blowing up balloons in an artery. I talked about the volume of the balloon with respect to time. If you were my Algebra 2 Honors student, you might remember it. You might not. I don't know. Not too bad though, right? Just compose the functions. So what if you had been asked to interpret a result? Okay, so you will be asked to do that on your test. Just like yesterday when we were composing and we were talking about was it the grain question? This one, to talk about what it means. You will need to be able to do that on your test and the test review. Okay. The number of bacteria in a container of leftover food stored in a refrigerator with T as temperature, N as number of bacteria. We're talking about degrees in Celsius, is modeled by this function. So the number of bacteria with respect to temperature, not time, is this quadratic. When the container is removed from the refrigerator, the temperature changes according to this linear function. Of course, that wouldn't happen in the real world. Does anybody remember how temperature goes up and comes down? It's exponential. Newton's law of cooling and heating. But anyway, they've told us how this works. So this is the temperature over time function. Time in hours. Find a composite function. So we're going to do n of t of little t and explain its meaning in the context of the scenario. Well, look at it. Time is the input. Number of bacteria is the output. That's the meaning. Well, let's find the function. So where function n had its capital T's, we'll have some parentheses. And in those parentheses, we will drop in the temperature over time formula. And I'll be honest with you, I don't feel like cleaning that up. I'm going to leave it just like that. I don't feel like foiling and distributing and combining vectors. It's not worth it. Just gives us an opportunity to make an algebra mistake. Let's just leave it like that. It says explain the meaning in the context of the scenario. The meaning is, or we could say something like this function shows how many bacteria are present as a function of time. So you want to know how many bacteria there are? Oh, how long has it been sitting out? Enter example B. Find the number of bacteria present in the food after the container has been sitting out for 2 hours. That's time equals 2. So this function, whose input is lowercase t, all those t's become 2's. So our number of bacteria after 2 hours is 60, and then we have 5 times 2 plus 3 squared minus 140 times 5 times 2 plus 3 plus 76, and it would be insanely big brain of me to say this number without, any hesitation, but instead, boop, I'm gonna put on a calculator because Well, I got nothing to prove. 60, and then what number is that? 13? Minus 140, 13 again, plus 76. There you go. 8,396 bacteria. And because I'm a big old nerd, I might as well tell you that 2 hours at room temperature, that food is still safe to eat.